Welcome to experiment number 3, and today we will test the half-wave rectifier with the RL load. The objectives of these experiments are: number 1, to simulate the half-wave rectifier with RL load using the PSpice software. Number 2, to utilize the software to observe the behavior of half-wave rectifier with RL load. For this experiment, we are to reconstruct this design circuit using PSpice. We will use a 2 ohm resistor, 0.1 Henry inductor, D-break for diode, and V-sign as our AC voltage source. For the frequency, we are given a value of 0.377. Using the formula omega t equals to omega L over R, we came up with a frequency of 60 Hz. So the frequency of our AC source is 60 Hz. Now let's create the project. File, new project. Let's name the CXP3HWRL. Create blank project. Okay. Now let's create the circuit. Go to place, PSpice component, resistor, inductor. Let's search for D-break, PSpice component, search. Let's search for D-break. We will use diode breakout device. Then let's search for V-sign. We will use transient sine voltage source. Then let's connect the circuit. Then let's place ground, 0 capsin. For the value of the resistor, 100 ohms. Inductor 0.1 Henry, V amplitude 100, offset 0, frequency 60 Hz, AC 0. Let's rename our AC source to VAC. Then let's create a new simulation profile. EXP3WRLS. Then choose PSpice AD. For our simulation setting, we will use time domain transient analysis. And for our run time, we will input 16.67 milliseconds. Then our maximum step size will be 10 microseconds. And click apply. Okay. Then let's run PSpice. In the simulation, our first trace will be the current waveform in R1. So in the add traces, let's click IR1. Here is the current in the resistor waveform. Now let's measure the peak current in the resistor. Go to the waveform, right click, cursor on. Then let's place the cursor at the peak of the waveform. From there, we recorded a value of 928.599 milliamperes. We can also observe in the simulation that the current in R1 rises up, and after it reaches its peak, the current decreases to a value of 0. The first value of omega t, or frequency that results to 0 current, is called the extinction angle beta. To get the value of beta in degrees, let's go to plot, axis settings, axis variable. Then let's modify the trace expression to time times 60 times 360. With the modification, the time or the x-axis is converted by the factor of 60 since our frequency is 60 Hz. Then it is converted to degrees by the factor of 360. Now let's place the cursor at the point where current reaches 0. By placing the cursor at the point where the current reaches 0, we recorded the degree value of 200 degrees. Now to get the value of beta in radians, let's modify again the time expression. Go to plot, axis settings, axis variable, then since 360 degrees is equal to 2 pi, let's change 360 to 2 times 3.14159. Now the time expression is converted to radians. Let's place again the cursor at the point where the current reaches 0. By placing the cursor at this point, we recorded the value of 3.49 rad here with the gathered values of beta in degrees and in radians. Let's compare it to our calculated values. Here's the analytical solution wherein we are given a value of 0.1 Henry for our inductor, 100 ohms for our resistor, Vmax of AC is 100 volts, then frequency is 60 Hz. Using the formulas, we have an impedance of 106.87, degree of 0.361 rad. Then substituting the values in the current formula, we came up with 0.936 sine omega t minus 0.361 plus sine 0.361 multiplied to e raised to negative omega t over 0.377. Replacing omega t by beta in the current formula, we came up with the calculated beta equal to 3.5 in radians. In comparison, we measured the beta value of 3.49 in radians and 201 in degrees. Then our calculated beta value is 3.5 in radians and 201 in degrees. We can say that the measured beta values is nearly accurate in comparison with the calculated values. Now let's test the Rms current in R1. Add trace, Rms, click IR1. So here is the Rms current waveform in the circuit design. Now let's measure the peak Rms current. Let's go to cursor. Then let's place the cursor here at its peak. From there, we recorded a peak Rms current of 680.130 milliamperes. Then let's measure its true value at the end of its waveform. From there, we recorded the value of 468.085 milliamperes. Now let's compare it to our computed value. To calculate the Rms current, IRMS is equal to square root of 1 over 2 pi, integral of I squared omega t d omega t from 0 to beta. By substituting the values, we came up with a calculated Rms current of 474.216 milliamperes. In comparison, using the PSpice software, we measured an Rms current of 468.085 milliamperes, which is less than but near to our calculated Rms current of 474.216 milliamperes. For our third test, let's go back to the simulation. Then we will measure the average current in R1 AVG. We click IR1. So here's the waveform of the average current in the resistor. Then let's measure its peak value. Right click, cursor on, place the cursor at the peak. From there, we recorded a value of 604.776 milliamperes. Then let's measure its true value at the end of its waveform. From there, the measured average current in R1 is 303.874 milliamperes. Then let's compare it to our computed value. So for the average current, the formula is 1 over 2 pi multiplied to the integral of I omega t d omega t from 0 to beta. By substituting the values, we obtain a calculated average current of 309.526 milliamperes. In comparison, using the PSpice software, we were able to obtain a measured average current of 303.874 milliamperes, which is less than but near to the calculated value of 309.526 milliamperes. We can say that differences from the measured and computed values were expected, since in the computation, the value of the diode was not used. However, the differences in the results are tolerable, since differences are always present in comparing theoretical and actual circuits. We also found out that we can obtain such values by using the PSpice software.